So for this video, it's certainly worth emphasizing here that not only does vintage tube-based equipment contain high voltages, and of course anything that's AC mains or line operated as well, but if you see me doing something potentially foolish, understand that I've already measured everything off camera and know that it is what I'm getting into. So I know what I'm doing. You may not. If you don't, do not attempt to replicate anything you see done here. So the purpose of this video is not to show you someone building an unopened Heathkit IG102 RF signal generator, nor is it a troubleshooting video in particular, nor are you going to see me solder capacitors and desolder stuff, because I assume you know how to solder. Probably if you're using an RF signal generator or plan to, it's probably already in your skill set. Now I'm going to do three things in this video. First of all, I'm going to show you piece by piece exactly which pieces I chose to update in this IG102. And there's maybe half a dozen to a dozen of those, and we'll quickly run through them one by one. I'm also going to show you which pieces I didn't touch, and related, which pieces I think have the status of unobtainium, and which don't. And finally, at the very end, I'll just touch on my main pet peeve with the IG102. So wait till the end for that. So without further ado, here we go. First of all, and perhaps most obviously, I replaced the two connectors on the front, which used to be this, which is sort of an old-style microphone connector that Heathkit used in both positions. Fortunately, the hole in the panel for this is exactly the same size as the hole for a modern BNC connector, and so that's what I did there to make it more practical to use. Any 60-year-old piece of test equipment is likely to have a old, crusty, petrified line cord, so of course a brand new polarized line cord for safety. In the 1960s, Heathkit was not known for adding line fuses to their equipment, so I did. This is just a glass instrument fuse holder with a slow blow fuse in it, again for safety. Looking at the AC input section of the IG102, the original kit came with a couple of these .02s caps. These are obviously disc caps. Notice they have no voltage rating either on the cap itself or in the parts list. So they're just .02 discs as far as I'm concerned, and these were wired line to ground and neutral to ground, and they're meant for RFI suppression. In other words, to basically dump to ground any RFI that happens to come in over the line cord. It's well intentioned, but since these are really not safety capacitors, I decided to replace these with official Class Y1 safety capacitors, which are meant for that kind of service. The other thing, by the way, is I reduced these from .02s to .01s because, first of all, that's what I had, and also that has the other beneficial side effect of further limiting, due to their increased reactance, the amount of line voltage that they pass, or at least the line to ground one will pass onto the metal chassis, because keep in mind this is, after all, a 2-wire AC signal generator, so there will be a teeny weeny amount of AC line voltage present on the chassis. And so one could in fact make the argument to not have the line to ground cap and only put a neutral to ground one. And so tell me what you think about that. By the way, hiding behind here is an NTC, a negative temperature coefficient resistor, which is basically there from line to load and limits inrush current. Again, I have a bunch of those, and on tube-based equipment I tend to put them in, and they limit inrush current to the filament when you first turn the thing on cold. While we're on the topic of the power entry wiring of the IG-102, I want to digress a little bit and talk about questionable choices Heathkit made, at least by modern standards, perhaps not by the standards of the early 1960s. Nevertheless, Heathkit, of course, chose to go with a 2-wire line cord here on the IG-102, and as I just mentioned, chose to put, in their case, 0.02 microfarads between line and chassis and neutral and chassis. Notice I don't say line and ground or neutral and ground. It's line and chassis and neutral and chassis. And this is because there's no ground. It's a 2-wire line cord. In particular, and these were done for RFI suppression, of course, but in particular, the problem with having the line to chassis here, the hot side to chassis, is that that capacitor, and whether it's a safety cap or the original cap, makes no difference, that capacitor will still pass a small amount of AC, small because its reactance is kind of high at that frequency, a small amount of AC to the chassis, which is now effectively at some voltage with respect to ground or the rest of the world. And I thought it would be interesting to measure that. And so I put an alligator clip onto the metal chassis, and here's my multimeter on AC volts. So the red lead goes here. The orange lead is a banana plug, and there's a reason I made it a banana plug at the other end, because I'm going to plug it in to ground. And so when we connect this through the multimeter to ground, we should see at what potential the chassis is living. And we'll do that right now. And I'm simply plugging it into the grounded pin of an AC outlet that's nearby, which I know is obviously properly grounded. And we get 62-ish volts. So right now there's 62 volts that would be I would be subject to if I were standing on a wet surface or otherwise grounded, and I touch the chassis. Obviously, I can touch the chassis, and I'm not going to feel anything. It's not going to electrocute me for a reason. Nevertheless, the question is, is this a good thing? By the way, notice that I have my BNCs disconnected, so the chassis is just there, sort of floating in midair at a 62 volt potential. Another thing I want to see is how much, if I were to touch this and be grounded with my other hand, how much current could potentially flow through me. And so that's fairly easy. I won't touch it. What I'm going to do is simply unplug this, switch this to milliamps, AC milliamps, switch my input plug to the milliamps microamps jack, and now again I'm going to plug it into the grounded outlet. There we go. And we have 0.6263 milliamps, so this makes it safe to just go to microamps. So about 630-ish microamps. So this is the short circuit current that is passing right now, AC current that is passing right now through that, well, in my case, 0.01 microfarad safety capacitor to the chassis and then onto ground. This is a very, very small amount of current. And in fact, if I were to touch or even connect either BNC, which is going to my scope, to either BNC connector, which are of course connected, their ground's connected to the chassis, that current immediately will get bypassed to the ground on my scope. And so it will no longer flow through the alligator clip. At least most of it won't. Do we really want 630 microamps potentially surging through you if you touch this and are grounded, or simply have 62 volts of potential? By the way, just as an aside, it's not, of course, not necessary for this unit to be on. for this to be the case, because this has nothing to do with the power switch. It's going straight from the line cord through the capacitor to the chassis. How to fix this? Well, there's two things one could do. Let me unplug that first of all. Or I can go back to volts. First thing I could do, of course, is to have a 3-wire line cord. Okay, here's my 60, in this case 60 volts again. Okay, 60 volts right now. I could put in a 3-wire line cord, and this is probably what I should do. The other thing I could do is to remove the one safety capacitor that's going between line and chassis. I think it's probably better to simply put in a 3-wire line cord on this unit, and then just take care and make sure if I ever do use this to inject a signal into, say, a hot chassis radio, to be very careful of how I connect it up. Also, having a 3-wire line cord will make the fuse much more useful, because should there be a fault, in an unlikely event that the hot side here directly touches the chassis somehow, and so it's going straight to the fuse, it's not likely, but suppose there is, or on the other side of the fuse the hot side gets shorted to ground, the fuse would not blow right now, but it will blow if I put a grounded line cord on. So that's probably what I'm going to do. Interestingly, although this is of course a tube-based RF signal generator, Heathkit didn't use a tube for the main power supply rectifier, nor did they use a selenium rectifier. They used a modern silicon diode, which probably was modern for the early 1960s. This was the original Heathkit part number 5727, which maps to cross-references to a 1N4005. So basically your run-of-the-mill 600 volt 1 amp diode. I replaced this with a full wave bridge, mostly because I have a pile of these full wave bridges, and maybe it'll reduce the ripple a little bit. There's a better view of the full wave bridge. Again, these are 600 volts at 3 amps. The notched end is the positive output, the opposite end is the negative output, and the two middle ones are your AC input. So here's the power supply section of the IG-18, and as I said, I converted the B plus half wave rectifier here to a full wave rectifier, and the way to do that is rather simple. Your full wave rectifier looks like this. This gets cut. Here's where you put one AC, other AC, plus out, minus out, which goes to ground. So this doesn't exist. And there's of course 4 diodes in there, and that's all you do. The 2 B plus filter electrolytic caps were in a single can, so here are the 2 plus sides and the 1 minus sides, and these were 20 and 20s. These, of course, were replaced by 2 discrete 20s at 250. This is the 2200 ohm 2 watt resistor 10% that Heathkit had originally designed in to the B plus power supply. And when I measured it, it had drifted quite a bit north, well outside of its rating. So I replaced it with a 2200 ohm, 5% I believe, metal film resistor, which is 2 watts, and as you can see, quite a bit smaller. And it runs quite a bit hot, but that's why you see the alligator clips across here, because I decided to see just how hot this is running. So I'm actually just measuring the voltage drop across this resistor, and it's dropping 32 volts. So 32 volts across 2200 ohms is a little less than half a watt. So yeah, it'll do just fine. This beautiful 0.1 at 200, which is part of the audio oscillator circuit, of course gets replaced by a 0.1 at 400. And this 0.0047 at 600, part of the audio oscillator, gets replaced by exactly the same thing, but more modern in a polyester. This 0.022 at 400, which served to protect the audio input and output jack, gets replaced by basically an identical yet modern cap. And this 0.05, also part of the audio in and out switching circuitry, gets replaced by a 0.047 polypropylene. In addition to the disc capacitors, which were not replaced because they're typically fine, there are two capacitors here that I simply didn't want to touch at all. This little guy that looks like a tiny resistor is really a 2.2 pico molded phenolic, is what Heathkit calls it. So it is a cap. It's a very small cap, but it is a cap. And also this 4.7 pico ceramic was left in place. These two work perfectly fine. The number 47 pilot light bulb, which sits right behind the beautiful little red LED lens on the front, was actually working, but it had gotten blackened over the decades, so I decided to simply replace the bulb. Beautiful incandescence. None of this LED rubbish. It's probably worth talking about the unobtainium parts, starting of course with the main two-section air tuning capacitor. Heathkit does not specify a capacitance for either of the two variable sections here. So be careful not to hurt it, and in particular not to bend the plates so they should never touch. Unobtainium are the band A, B, C, D, and E coils that form the oscillator for those bands. These guys are fragile, so when you're recapping and screwing around inside, be really, really careful not to damage these. And there's a little 1 to 10 picofarad trimmer cap hiding out right down here. This is actually the main calibration for bands A through E, so don't damage it. There's a screw on the other side which you use to do final frequency adjustments if you want. And what looks like a squiggly piece of bare wire might be strange to call unobtainium. This is in fact the main frequency determining coil for band F, the highest frequency band. This is obviously an inductor, and it actually came pre-made along with a tap wire pre-soldered as part of the kit. So you did not have to wind this yourself. It came pre-made and pre-tapped. So that might tell you something. Here it is, in fact, in the parts pictorial. So it comes completely pre-assembled and pre-wound. In the parts list, it's simply listed as band F oscillator coil. So there's absolutely no value listed for this, and in fact it varies because the way you can do fine adjustments to the band F calibration, according to the manual, is to squeeze the coils together a little bit or to spread them out a little bit. And I've tried this, and it's actually no fun, so be careful, and I'm still going to list this as unobtainium. Could you duplicate this? Perhaps, but its inductance is not specified, so hopefully you'd have another one to measure against. Also unobtainium is this little unassuming guy that looks like a tiny power transformer or an audio output transformer. It is neither. This is a tap, a choke with a tap, not necessarily a center tap. It is only listed as oscillator transformer because it's part of the nominal 400 hertz audio oscillator section, but its inductance on its windings is absolutely unknown. There are only 2 tubes in the unit, and they are absolutely not unobtainium. They're quite obtainium. They're very common. The 12AT7 on the left, that's used for the RF oscillators, both the band A and through E and the F oscillator. That's why it has 2 sections. And then on the right, the 6AN8A, which is used for, half of it's used as the audio 400 hertz oscillator, and the other half is used as the final amplifier. And I'll leave you with the oscilloscope beauty shot of the output. The purple is, of course, the RF, which is running at about 100 megahertz, modulated by the 400-ish hertz audio oscillator, which is the yellow sine wave. And you notice how they line up pretty nicely, so that when the sine wave is at the peak, the amplitude of the RF is at the peak, and so forth. The oscillator is running right now at 410 hertz. One last thing I wish were different about the IG-18 is the way it handles the internal modulation. Here, the switch is in int mod AF out, so it's being internally modulated by the 400-ish hertz that you see. So that's, again, the purple trace that's properly AM modulated. And then the yellow trace is, in fact, the 400-ish sine wave from the internal generator that is doing the modulating. I really wish there was some way of setting the internal modulation level when you have it in internal modulation. If I turn the AF potentiometer, I can change the level of the output audio signal that's being used, but it has no effect on the internal modulation, which is still nominally 30%, although I kind of question that. So there's no way of varying the level of modulation when using the internal 400-ish hertz audio generator. When you have it on external modulation and you're using the AF input as an input, then that does go through the same potentiometer, and that does affect the modulation level if you're using an external modulation, but not if you're using internal. Here, basically the same thing, except instead of using the internal 400-ish hertz modulation from the IG-102, I'm feeding in an external modulating signal through the AF connector, and I have the switch set to external mod, and in this case it's a 400 hertz spot-on sine wave. But here, when I turn the external modulator AF out control, I actually can control the level of modulation.